times pi r squared. So I enclosed, which is not the same thing as I, is going to be j times pi little r squared, isn't it? And why is j going to be, or why is I enclosed going to be that? Can somebody tell me why? Why I enclosed is j times pi r squared. Well, if j is if I is the total, if j represents the current per unit area, pi r squared represents the area. So I have units of, so j has units of current per area. So then what I need to do then clearly is to get current is multiply by an area, because then my areas will cancel and then I'll just have current. So current J times an area is going to give me what I need for that. So that's actually going to be my I enclosed. But then I can make the substitution here that J is equal to I over pi big R squared. And so then this is a perfectly valid way to write I enclosed. But then another way to write I enclosed is like this. Another way to write I enclosed is where we make the replacement of J with I. So J, that whole expression for J can come right here and take its place. And then I have something very useful, because then I have something that's going to set me up to do Ampere's law precisely for this kind of a problem. Okay, so I've got I enclosed, and that's going to be equal to I over pi big R squared, because that's my J, and then I'm going to have pi little r squared on top, because that's that, okay? So then we've got some things that are going to cancel. Pi's are going to cancel, and I'm just going to have that's equal to I little r squared over big R squared, okay? So then that's I enclosed. I over with little r squared over a big R squared. So now we can do Ampere's law. And let's do Ampere's law. And this is gonna hold for any point inside of this cylinder. And what is this gonna be for? So I don't want to get too far ahead of myself. So let's write Ampere's law again. So what does Ampere's law tell us? It's the line integral of B dot dl, and what does that equal? U naught over I enclosed, right? Okay, U naught over I enclosed. So then we've got our Ampere's law, and we know what B dot dl equals. This is actually an easy integral, because my integration path here, I'll just go right back to it. My integration path is 2 pi r. That's the total amount for any given r, whether I go out to here or out to here. Whatever my r is, it's 2 pi r. That's the length of my path, because I'm doing a dl here. I'm going along dl here, and I'm counting out all of the current that flows out of that dl, whether r is here or maybe it comes out a little further. And then I'm going to have a little more I enclosed. But regardless, I have the answer for any r, not just one point. Any r from 0 all the way out to here. Does everybody see what I'm doing there? How that works? Anybody confused by this? Okay, great. So then we've got, now we've got our answer for this side. So it's going to be B times 2 pi r. And then we know I enclosed is going to be this, so we got mu naught I, little r squared over big R squared. So then we've got B times 2 pi r, mu naught I, little r squared over big R squared. And then we're going to divide out this 2 pi here to get my B field, 2 pi r. And so my B field for this, for points inside, so for R inside R less than big R, my B field then is equal to here, because I just divided by 2 pi r, so now I have my B field. Mu naught I over big R squared, and then there's a 2 pi here in front. We'll put it up in front. So 2 pi stays, and then one of my r's cancels. So I have a single r on top. So that's interesting. So that means that my B field is going to increase linearly with R. It's going to go up linearly because R, this is all a constant. This doesn't change, but this can change. So my B field is going to go like a line. And what's it going to be at the very center, interestingly enough? What's it going to be? What's my B field going to be at the very center? What? 0, which is so counterintuitive. If you've never done this problem before, and it's like, just guess what the B field's going to be at the center. I don't know. Is it going to be maximal? Maybe, probably. I don't know. Turns out it's 0. That's crazy. It's really interesting. So it's like, now that we've got this Ampere's law, we can do some pretty powerful stuff with it. We can find things that like are not so simple. Okay, so that's inside the conductor. Now we've got the B field at any point inside the conductor. What about outside of the conductor? So outside of the conductor is a little bit easier because outside of my conductor here, I've got, I can choose any path that I want. I can make R as big as I want, but I'll just make it out to here. Outside of the conductor, I enclose the total current I. So I enclosed, so for outside conductor, outside of conductor, where R is greater than big R, I enclosed just equals I, and I don't need to worry about that current density anymore. I just use Ampere's law in its basic form. I'm going to have this, so it's going to be B, line integral of B dot dl is equal to, and then I'm going to have mu naught I enclosed, and then this line integral here is going to be, again, 2 pi r, because r is just bigger now, but it's still 2 pi r. It's just a bigger r. That's going to be my line integral of dl, 2 pi r. So then my outside of the conductor, then B 2 pi r, that's my B dot dl, equals mu naught over I enclosed, right? So then I just divide by 2 pi r. And so the value of the B field for B outside conductor, that's going to fall off as R gets bigger. So as R gets bigger and bigger and bigger, this gets smaller and smaller. But it doesn't fall off as quickly as a point charge. Remember, a point charge, the B field always falls off as like 1 over R squared, because you've got that factor of R squared in the denominator. For this conductor, it's falling off way slower. It's linear. But that kind of makes sense because it's like, well, okay, we've got an infinite line of charge running past here. it probably would fall off slower. This got a lot more, but now we have a precise answer for our intuitive thinking. So that gives us a really nice solution here for working this kind of a problem with Ampere's law. We can figure out the B field at all of these different points inside of a conductor, just like we could do with Gauss's law when we had these complicated arrangements of charges being located in different places and figuring out what the fields were. Okay, so is this actually important? Yes, it is, because you have coaxial cables with currents running in different directions sometimes, and you can do a lot of useful stuff with electronics with an understanding of how to harness charges. Microelectronics use currents going in all different directions. Admittedly, the currents are usually a lot different in tiny electronics. Okay, they're using things that are more complicated, like voltage gates and diodes and things like that you'll learn about if you do a double E. You'll learn about that stuff, and it's really cool stuff to learn about, by the way, too. But the basic principle is that, yes, this is important, too. So it's really cool to see. So outside the conductor, the magnetic field is the same as a long, straight conductor carrying current I, independent of the radius R over which the current is distributed. And so then the magnetic field outside any cylindrically symmetric current distribution is the same as if the entire current were concentrated along the axis of the distribution. Okay, so we found an analogous result. You did this last quarter, in which you found the electric field outside a spherically symmetric charged object is the same as though the entire charge were concentrated at the center. And that's kind of a useful, the cool thing about that is that kind of reminds us of gravity then a little bit too, doesn't it? Because it's like the Earth is a spherically symmetric mass object, and the mass of the Earth is the same as if it's concentrated about the center. So there must be some kind of a relationship to gravity and electromagnetism, because that doesn't just happen on accident, right? It's kind of crazy that we don't have these things unified yet when we have something that's so similar. We have a spherically symmetric distribution of mass, spherically symmetric distribution of charge, behaves as if it's all about the center. And then we have this conductor thing here too, acting like that for the magnetic field. And we do know how magnetic fields and electric fields are related. That's coming a little later, but one person's electric field is another person's magnetic field because they're part of the same object. I've said that a bunch of times, but it's still worth saying.